Hi everyone, it's Mr. Srikanth here, and I'm going to talk through the examples that are on the Rules of Indices set of questions and pages on the booklet. So hopefully this will enable you to crack on with the practice questions. So here we go, first with the key points. So you can see at the top there, the first key point is the multiplication rule, that if you're multiplying a pair of indices where the base number is the same, then you can add the indices. And the reason for that is, if I do it with an example, a cubed multiplied by a squared is, well, a cubed means a multiplied by a multiplied by a, and a squared means a multiplied by a, and this is being multiplied together. So you can see there that in total you have 5 a's all being multiplied together, so that's a to the power of 5, and then you can extend that rule towards any indices. It doesn't have to be 3 and 2. Obviously the next rule, this rule here, is just about the inverse operations. So if you're dividing, then you would obviously subtract. There's a few different ways I could explain that. I'm not going to go into that now. You should hopefully have come across all of these rules in GCSE anyway. The third one, fairly straightforward to show you why that's true. That's using the same indices I used before, 3 and 2. This time I've got a cubed squared, and a cubed squared means a cubed multiplied by itself. And so you can see there that if I then use the rule above that we went through at the start, then you're going to end up doubling the 3, adding 3 to itself. So you're going to end up with a to the power of 6. And obviously the faster way to do that is to multiply the 3 by 2. The 3 by 2 there at the start, that's quicker than writing it out in this way. Okay, then you've got a to the power of 0 equals 1. I'm going to look at that in the first example in a moment. You've got the nth root when it's a to the power of 1 over n. It's important to notice here, and I'll come back to this point later on, that you've got a numerator of 1. And I'm actually going to recommend that you don't so much learn this rule, the next one, as learn that you can always write an index like this as this. And that's quite an important point, and again I'll come back to that in one of the examples later on. This one, so the next one, with the negative index is 1 over. I will look at that in example 4. And the square root, the final one here, I actually disagree with. I would say that this is wrong, and I have emailed the exam board to say so, and I'm looking forward to their reply. I've done that today. If you ask me, I will say that the square root of 16, written with that symbol, is positive 4. And that's because this symbol is the non-negative square root. And it's for that reason that when you write out the quadratic formula, you need a symbol that looks like this. I'll do it in the corner here. You need a symbol that looks like that, an add or a subtract in the quadratic formula, because the square root symbol only refers to the positive one. So you would either add that or subtract it in order to get your solution. However, with Pythagoras, you don't need a symbol like this, because Pythagoras is in reference to finding a length, and lengths can only be positive. And so in that case, where shall I squeeze this in? Up here. In that case, where you've got c is the square root of a squared add b squared, no need for any positive or negative symbols, because the length has to be positive, and so this symbol is sufficient. Okay, let's move on to the examples. So, evaluate 10 to the power of 0. Now, of course, using the key point on the previous page, you could just write this down as 1, and that is what I would expect a student in A-level to do. However, if you were to be confused or forget this rule, then it's very straightforward to work out why that's true. There's a few different ways you can look at that. You can think of it as a pattern. So you could think about this sequence. And this is 1000 because it's 10 times 10 times 10. This is 100. This is 10. And you can see here that what's happening each time is you're dividing by 10. And so for this final one, you should still need to divide by 10 and you would get 1. That's one way of thinking about it. Another way of thinking about it is to say 10 to the power of 0, using the division rule, is 10 to the power of, let's say, x divided by 10 to the power of x. Why does that work? Well, we know from the rule on the previous page about division of indices that you would subtract these two indices. So you do x subtract x, which is 0. So you've got 10 to the power of x divided by 10 to the power of x equals 10 to the power of 0. And you know that if you divide anything by itself, then the answer is 1. So this must be equal to 1. So there's a couple of different reasons or explanations as to why 10 to the power of 0 equals 1. Obviously, as I say, I would expect an A-level student to just know that 10 to the power of 0 equals 1 without having to think about it very much. Okay, example number 2. So evaluate 9 to the power of a half. Well, 9 to the power of a half is the square root of 9, and that is positive or negative 3. Again, if you're not sure why that is, the easiest way to think about that is to think, well, what happens if I do this calculation? Using the rule of what to do when you're multiplying indices, I know that this should be 9 to the power of a half add a half, which is 9 to the power of 1, which is 9. But this is something multiplied by itself. And when I multiplied it by itself, my answer was 9. So then I'm thinking about what it is that I can multiply by itself to get an answer of 9. The answer to that is 3 or negative 3. So you can see why that would be the square root. Again, I would expect an A-level student to be fluent in being able to write 9 to the power of half as positive or negative root 9. Right, I said I would come back to the rule which the key point stated as being to the power of m over n. And what I wanted to show you there is that we can figure out an easy way to work this out by breaking 2/3 down into a pair of numbers that have been multiplied together, both of which are simpler numbers than 2/3. And the easiest way to do that is to use 1/3 and 2. So hopefully you're looking at that and you agree that 1/3 multiplied by 2 is 2/3. When I write it in this way, I always do the smaller number first, and there's a reason for that. That's because I'm going to break down the index from the question in this way, in the order that I've written it. So 27 to the power of 2/3 is in fact 27 to the power of 1/3 all squared. Why is that? Well, because you know that you can multiply the indices when you have one index followed by another index. And this is now fairly straightforward, because if you think back to example 2 just now, 27 to the power of a third would be the cube root. 9 to the power of a half was the square root of 9. 27 to the power of a third would be the cube root of 27. So that's the cube root of 27 squared. The cube root of 27 is 3. So that's 3 squared. So this is 9. Okay, example 4. 4 to the power of negative 2. Well, 4 to the power of negative 2. Again, the quickest way, and what I would expect from an A-level student, is to say, well, that's just the reciprocal of 4 squared. And I know 4 squared is 16, so that's 1/16. But again, if you can't remember the rule, then it's fairly straightforward to come up with a calculation where the answer is 4 to the power of negative 2. Easiest one, I think, is probably this one. So I'm using my division rule, and I know that if I've got the same base number, so 4 and 4, then I can just subtract the indices. 0 subtract 2 is negative 2. So hopefully you're happy with this claim that 4 to the power of 0 divided by 4 squared is 4 to the power of negative 2. And then the good thing is, I know what this is. Anything to the power of 0 is 1. And I know what this is. 4 squared is fairly straightforward. 1 divided by 16. And 1 divided by 16, the easiest way to write that is 1 divided by 16 like this. So this is the same as 4 to the power of negative 2. And if you think back to example 1 when I talked about 10 to the power of 0, another way to think about this would be to say 4 cubed, 4 squared, 4 to the power of 1, 4 to the power of 0, 4 to the power of negative 1, 4 squared. No, 4 to the power of negative 2, sorry. Four cubed is 4 times 4 times 4, which is 64. 4 squared is 16. 4 to the power of 1 is 4. What's happening each time? I'm dividing by 4. So if I keep on dividing by 4, I get 1. Divide by 4 again, I get a quarter. Divide by 4 again, I get 1/16. 3 different ways to work out that 4 to the power of negative 2 is 1/16. The way at the top of the page is the fastest way. Okay, simplifying should be a fairly straightforward skill for you on this particular type of example, but I'll break it down just so you can see where everything comes from. This is 6 divided by 2 multiplied by x to the power of 5 divided by x squared. If you think about covering up the original question, so if I just cover that up for a moment, hopefully looking at what I've written on the right hand side, you can see that the answer to that is 6x to the power of 5 over 2x squared. You know that to multiply fractions, you can multiply the numerators and multiply the denominators. So you should hopefully be okay with the fact that these are equal. And then you can see that this first part is just 3. And using the rule about division of indices, x to the power of 5 divided by x squared is x cubed. So this would be 3x cubed. Okay, on to example 6. Example 6 is fairly similar to the last one, apart from that at the very start I'm going to simplify the numerator, which is x to the power of 8. I'm using the multiplication law of indices there. And then I've got 8 to the power of 8 divided by x to the power of 4. Division of indices rule is that I can subtract the powers, so that's going to give me x to the power of 4. Okay, example 7, 1 over 3x. Well, again, I'm going to start off by saying that this is 1/3 multiplied by 1 over x. Again, I'll cover up the left-hand side and just remind you that by multiplying the numerators, I get 1, and multiplying the denominators, I get 3x. So you should be able to see that that is the same as 1 over 3x, but each part of that, 1/3 and 1 over x, is slightly more straightforward. Okay, and then we know that 1/3 is just 1/3, but from our earlier rule, I think it was example 4, we should know that 1 over x is the same as x to the power of negative 1. And so to write 1 over 3x as a single power of x, I would get 1/3 x to the power of negative 1. Okay, And then on to the last one, which is 4 over the square root of x. 4 over the square root of x, well, you already know from what we've done earlier that root x is the same as x to the power of a half. And if I write this like this, then hopefully you can see, if I draw my rectangle again and cover up the left, that 4 multiplied by 1 will give me the numerator of 4, and 1 multiplied by x to the power of a half will give me the denominator of x to the power of a half. Now, the left-hand side, that's nice and straightforward, that's just 4. The right-hand side, 1 over x to the power of a half, well, if it's x to the power of a half, but the reciprocal of that, the reciprocal is the negative power. So that's negative a half. And so we get 4x to the power of negative a half. Okay, so that's all 8 examples completed. So now you can complete the practice questions 1 through to question 10. They obviously get quite tricky towards the end, and then don't forget to mark your work. Any questions, feel free to drop me a message on Firefly or by email, and I will try and get back to you. Thank you, bye bye.